Okay, lesson 19. So transformations of exponential functions. All right, so let's just get our bearings here. Let's write down the equation that's on your formula sheet right there, right? So we've been doing a lot of this where it was y is equal to a f of x and then, or sorry, f of b, x minus h, and then plus k, right? So yeah, we've been doing like a ton of these things. This is actually just going to be like another version of the same thing now, but we're doing it with an exponential function. So here's how it's going to work. Instead of it being like an f of x part, it's actually going to be this. So here, I'll write this underneath so you can kind of see the similarities. So it's a is equal to, or sorry, y is equal to a, and then c, b, oh, that's not a b, b, x minus h, and then plus k. Can you guys kind of see the similarities there, like what's going on? So like the c is a new thing, but that's really just like part of our function. That's like, in the last one that'd be like 2 to the power of x or whatever, right? But it all looks kind of similar where we've still got our horizontal stretch. We've got our, or sorry, vertical stretch, I should say, vertical stretch. We've got our horizontal stretch. We've got our horizontal translation, and then we have our uh, vertical translation, right? So everything's the same, it just looks a little bit different here, right? Things are still backwards like they normally would, right? Like the horizontal stretch will be like the inverse of what that is, and the horizontal translation will still be the opposite sign of what it is. But yeah, so that's pretty much for the most part what we're seeing in all of this, right? We're still gonna have reflections all the same way too, right? But let's do some examples. I think this will make a bit more sense. So it says for the following exponential function, describe the transformations as well as any effects on domain, range, asymptotes, x and y intercepts, and end behavior. All right, so starting off with this guy. What I'm going to do first, let's rearrange this so it looks a bit more like our equation up that we just learned up there, right? So let's rewrite this as here we'll go negative y is equal to 10 to the 3x plus 9 minus 4, right? Just move the 4 over. And then just dividing everything by negative 1 or just, moving things around there. I think you guys read at this. Y would be equal to, and then we're going to have negative 10 to the 3x plus 9 and then plus 4. Okay, so from there I can see a few things, right? I can kind of get my bearings here for as far as what, well, here I'll write this out too. This is y is equal to a c to the power of b x minus h and then plus k, right? So there's some similarities going on there. So I can see from this thing, well, looks like I've got a reflection going on there, right? And if it's if a was negative, remember what happened there is that was a reflection over the x-axis, right? Like my whole thing will become, if they were positive, they'll become negative, like the y values, and if they were negative, they'll become positive. So that's gonna be a reflection over the x. I can see that I'm gonna have a vertical translation for up, but then this is a little messy up here, right? Well, we've still got that same thing where I can't see the b yet, right? My b value is not going to be 3 there. I have to factor out a 3 first. So like we've been doing for that before, that whole c to b thing. So we'll rewrite this a little different. We've got y is equal to negative. Here, I'm not even writing like this, negative and then 10 in brackets so I can see my a value a bit clearer there. And then, yeah, so we'll factor out a 3. So we've got 3 and then times x plus 3 and then plus 4. All right, so now it looks like I've got everything I need. So let's write out everything that we're doing here. So we have a vertical reflection in the x-axis. And that comes from our a value being negative, right? We have a horizontal stretch of, okay, so be careful on this one, a horizontal stretch of. So horizontal stretch of, I'm looking at, oh, where's my pens? 1 sec. I'm looking at this one right now, right? So you might be tempted to say a horizontal stretch of 3, but we know that that's not right, right? It's going to be the inverse of that. So it's a horizontal stretch of 1/3. Okay, next one, we have a horizontal translation of 3 left, right? 3 left. So it's going to be the opposite of that sign. It was +3, so now it'll be 3 left. Okay, and then we have a vertical translation of 4 up, and that's from that one. Okay, so that's all of our transformations there. Let's describe our domain and range and how that changed up. So domain and range, I'll write that over here maybe. So our domain in this case of this function will be, well actually, if you think about, just let's draw this for a second, right? The original function, just the normal, like, you know, y is equal to, let's make our c value like 10 to the x, right? Remember from last lesson, the way that would look would be something like this, right? Where it would have an asymptote at 0, it would still cross at 1, right? That would still cross at 1, but it would go up really fast from there on because it's multiplying by 10 every time. But that's the original graph, right? The domain of this original one was x, you know, is a member of the real numbers. It just goes on infinitely far to the left and infinitely far to the right. Actually, everything's still going to be the same here. Like, and that makes sense because there's actually no number for x that you could throw into this equation that would be a non-permissible value, right? We're not dividing by 0 and we're not taking the square root of a negative. So actually anything goes here. So we still got just x is a member of the real numbers. Nothing really changed up there. But now what about our range, right? So our range, well, let's just look at the original. The range would have been y has to be greater than 0, right? That's what it would have been on our original function there. Not including, it wouldn't be or equal to because it never does touch 0 and it has to be above it, right? In this case, what happened is that, you know, we moved 4 up because of that 4 there, right? So this whole thing, you know, that asymptote that was right at 0, that thing is getting moved 4 up now. So you might be tempted to say this. You might say y is greater than 4. But here's the thing. That thing did move up 4, but then remember, it also got flipped upside down. We had a reflection. We had a vertical reflection over the x-axis. So this thing would move up 4. Sorry, this is getting a little messy. I hope this makes sense. It moved up 4, but then this thing is actually flipped upside down now. Now it's actually going down like that. Probably not crossing where I had it cross there, but that's the idea, right? It's going to be at the point 4. It's going to be going down from there because it flipped upside down. So it's not greater than 4. It's actually going to be y is less than 4 for our range now. Okay, and then the next, it said asymptote. So normally the asymptote would be at the point y is equal to 0. Now it's going to be at the point, so horizontal asymptote will be at y is equal to 4 because the whole thing got moved up 4. Okay, now end behavior. So end behavior. Well, let's just again sketch this a little bit so we can see what this would look like. This would do something like, you know, if this was the point, like the line at y is equal to 4, then this graph would do, you know, something like that, right? Going down that way. So what you would say here then is you could say, well, low in quadrant 2, low in Q2, and low in Q4. And it's a little bit vague there, right? Because like, what do you mean by low, I guess, right? Because this had an asymptote at 4. And then, but then this one really is low in quadrant 4, right? Because this one goes really far down. But that's a general idea, just to kind of generally talk about the end behavior. When you get into calculus, we get a lot more specific about what we mean about that, but that's definitely good enough for now. Okay, the other part of this, now that we flipped upside down like that, we actually have x-intercepts and y-intercepts now, right? So this thing is going to cross. I think I'm definitely wrong here. It actually probably will be more like this, like down here by quite a lot, I think. And so there's going to be an x-intercept and there's going to be a y-intercept there. So let's see if we can figure those ones out. So let's write down our equation again. So, well, actually I'll do a little header there. So for the x-intercept, so the way this would work would be like this. We'd say, okay, well, for the x-intercept, then, well, here, let's write down the original equation. So the original equation there was 4 minus y is equal to 10 to the power of 3x plus 9. Okay, so if I want to find the x-intercept, that's when y is equal to 0. So I could throw a 0 into that. So we'll say, okay, well, that would just be 4 is equal to 10 to the power of 3x plus 9. And then here's the problem, right? I need to solve for x. How the heck do I solve for x when it's up in the exponent? That's actually a really big question because we haven't talked about that yet, right? We don't have the ability to do that. We're going to find out some ways, right? We could take, actually, when we get into the logarithms unit, we can solve it using logarithms. Or actually in the next lesson, we're going to talk about how to do it with just getting the same bases. But this one, we couldn't get the same bases anyway. So we're kind of, without logs, we can't really do this without logarithms. But one way we can always do it, we can graph it, right? I could graph the left side of the equation as, let's say, y1. I could graph the right side of the equation as y2. And then when I solve for things, remember, I'm looking for where they intersect. So I never wrote that down, but that's what you do. I don't, for the sake of time, I don't really want to do that, but yeah, that's what you do. You graph y1, y2, and you could always solve it that way, right? All right, so that's how you find your x-intercepts. Let's do y-intercept. So for the y-intercept is where x is equal to 0. So here, this is right. So your y-intercept. So we'd say 4 minus y is equal to 10 to the power of 3. And then what I'm going to do here is throw a 0 in for this, right? So 3 times 0 plus 9. So this would all simplify to 4 minus y is equal to 10 to the power of 9. Okay, so then rearranging this, I can get y. Let's bring the y over there, and we get 4 minus 10 to the 9. And that's actually a really, really small number. It ends up being negative. Make sure I get all my 9s right. 999, 9. How many 9s do I got there? 4, 5, 6, 7, 8. 8, and then 6. Right? Is equal to y. So yeah, I was really kind of wrong here, right? This thing would have actually crossed like way, way down here, right? Like way, or like really far down. But all right, so that's the idea on that one. So now, application. So we're going to get into a bit more into this actual equation here. This one actually is on your formula sheet as well. And if you guys have taken chemistry or parts of physics 30, then you would have seen this before. And it's a really famous equation. It's about exponential rate, right? So how fast things grow. So let's go through this in some examples here. So this equation, the way this works is you're going to have your value out front will be A, and that'll be your initial population. Which, if we're comparing it, right, this equation actually isn't any different to this. Y is equal to A C to the X, right? It's the same equation. They're using, at least they're using A for the first one, so that's the same. They're using B now instead of C, but it's the same idea. The only thing that's really different is we've got a fraction up here, right? So if we look at these things though, our B value, right, that would be like our A value in this one. Do you remember how that was always where it crossed the y-axis, right? So if this thing crossed the y-axis at 2, then that would be 2. Well, that actually kind of makes sense when it's saying like A is our initial population. That's where we are on the y-axis. That's where we're starting. So that kind of still makes sense with what we were doing, right? B value is going to be the rate that you're growing at. So if it was doubling, then B would be 2. If it was a half, like a half life, like we're going to do in a minute, then B would be a half, right? That's actually what you're multiplying the thing by every time. Okay. Yeah, it says X represents the unit of time if the period of time is 1. So in that case, what they're talking about there, X would be, this would be X, like the two of them together, right? T represents the length of time, and P represents the period of time, such as doubling time. So let's just talk about that for a second, because that can be a source of confusion. So Y is equal to a, let's say our number was like doubling. Let's say it was just this, where it was like 3 times 2 to the power of, and let's say it was 4 over 2, so it kind of matched this, right? Okay, well, what that's saying there is that the doubling time happens every 2, and then that could be like hours or days or whatever. And then the top number is how many days have actually gone by, right? So 4 days have actually gone by, and it doubles every 2 days. Then what you're really getting there, Y is equal to 2 to the power of, and then 4 divided by 2 would be 2. It means that 2 doubling times have happened. It means it's doubled twice, right? So this whole thing we're doing really simplifies back down to our original equation there. So hopefully that makes sense. Let's put some numbers in to see if we can make more sense of it. So this example, it says in 2001, the population of Sylvan Lake was 7,500 people. If the population increased at a rate of 4.5% per year, write an exponential equation to model the population growth. All right, so here's the idea. So we'll start off with Y is equal to A times B to the, and we'll just say X for now. Okay. We'll switch that up here in a bit to T and P in a different example, and it'll make a bit more sense. But for this time, we don't really need to. We'll see why in a sec. So, all right, here's the idea. So we're going to say Y is equal to, and then A is going to be our original population. That's like our y-intercept, right? If I was graphing this thing, that would be where we started, right? That's our A value. And we started at 7,500 people. So that's this number. So we're going to say 7,500 and then times, and then we got to make sure we get this one right. So what is the number we're multiplying by? It says that it increases at a rate of 4.5% per year. Okay, so what we'd be doing here then is we'd say, okay, well, one would just, let's say this for a second. If you had 7,500 and we multiplied it by 1 to the power of anything, right? I don't care what's up there anymore. Then we're just going to be where we started, right? That 1 just kind of gets us to our starting point. What I want to do is I want to say it's going to be 1 plus my percentage that they gave us, because we're increasing. So I'm going to write that as 0.045, right? That's how you write 4.5%. And move my bracket. And it's that squared, or not squared, sorry, to the power of X, just for now, right? Okay, so a better way to write that, like more intuitive way, would be like this. Y is equal to 7,500 times 1 and then just 0.045 to the power of X. So there's our equation. So we're good to go there now, right? So we can start putting in numbers for X, right, and seeing what it comes out as, or Y. So now it says determine the population in 2016. So let's do that one. We'll say Y is equal to our equation, 7,500 times 1.045 to the power of, and then, well, what's our X going to be? Well, it's the number of years that went by. So the number of years that have gone by would just be 2016. minus 2001, where we started, right? We started in 2001. So it's going to be 15. Okay, and if you just put this all in your calculator, make sure when it goes into your calculator that you are only squaring this part, or not, only raising this part of it to the power of 15, and not going 7,500 times this to the power of 15, because those will be different numbers. So it's only this part that's being raised to the power of 15, right? If you do that, you should end up with 14,514, and then that would be people. Okay, next one. All right, the population of mallard ducks in Canada can be represented by this function, where X is the number of years since 1975. So very similar, but it's asking us, is the population increasing or decreasing? And we can tell by our multiplier, right? The number that we're actually multiplying every time here, that number is less than 1. So that must be decreasing, right? This thing's going down every time. So this thing's decreasing. So less than 1, you could say, yeah. Decreasing because we call it B in this one, right? Yeah, B, could be C too, whatever. Decreasing because our B value is less than 1. It's also greater than 0 though, right? But yeah, that's the idea. It's going to be a fraction less than 1. Okay. The other thing that you should see from this thing is that what this is doing is every time it's giving us 95% of the original, right? Because if this was 1, that would just be 95% of this. And then the next time, if this was a 2, then it would be 95% of the next number, and then 95%, right, of every one of those numbers. So it's going down and down and down. This is really going down by 5% every time, right? So yeah, just take a look at, if that didn't make sense, maybe look that one over and try to make sense of what I said there. All right, B. How many mallards were present in Canada in 1975? So just plugging it all in, be the same thing as what we did above. So I'm not going to spend too much time on it. 1,731,000 ducks. All right. How many years passed before 1/2 of the population remained? All right, so let's write down our equation here that they gave us. So the equation is y is equal to, oh, sorry, I explained that one kind of funny up top too. I was able to tell from this one how many ducks were present in Canada in 1975. Really, because that's where we started too, right? So that really is just this number out front. So I could have put a 0 in there and got the same answer, but yeah, that's just the number. That's our y-intercept. Sorry. Okay, so sorry, carrying on. 1/2 of the population. So we'll say, here's our equation of that number. 0.95 to the power of x. Okay, and they're saying how many years passed before 1/2 of it. So the years passed, the time in this case is x, right? So they're saying, what is x? We got the same type of problem here where it's going to be hard to actually solve for x because we don't know how to do that yet. But I also don't even know what y is. But I kind of do, because it says 1/2 the population. So, well, if this is what I started with, 1/2 of that is going to be what y would have to be here, right? So, so what we can do is we'll just say, well, that number would be this. If you divide it by 2, that'd be 0.95 to the power of x. Okay, now, this is true, right? Because this number is 1/2 of that number, so we're good to go. You could, at this point, graph this and say, okay, y1 and, all of this is y2. It's going to be annoying, though, because, well, these numbers are huge, right? It's going to be hard to find my window settings. So what I would recommend to do here is divide this part out first. We can divide both sides by 1,731,000, right? Divide those on both sides. And we end up with, well, actually, this makes sense, right? That'd just be a half, right? A half is equal to, and I'm going to write this a little different for a second, is equal to 1 and then times 0.95x. I just want you to notice this for a second, that we started off with this number, right? Like all the way up there. And I said, okay, well, this would be a half. This also would have worked if I started out with 1, right? Let's just pretend for a second that 1 was my starting number, and then I ended up with a half. It doesn't actually matter. It's going to take the same amount of time for both those things to happen. So yeah, I actually didn't need to even start out with that big number. I could start with any number I wanted to. As long as this one was a half of it, then we're good to go. All right, so let's do this now. Now, if we graph this one, graph that side and graph that side, then again, I don't remember what it was, but your graph would look like this, right? So when you graph this guy, you'd have 1/2 would be a line going across right there. Oh, put straight. And the other one would be a line coming down like this. It would go down and cross. And it'd be right where they cross, it's your X value, right? It's this value that's going to be the one. Well, this would be a half. So it'd be the value that goes in there. So for the sake of time, again, like I said, I'm not going to do that one. You guys have done tons of those. So that's the idea there, though. All right. Next one. Radioactive decay or half-life. Okay, so this is really going to be similar, but like what we have now is we have our different version of the equation. Y is equal to A, B to the power of T over P. We've just really replaced the X with the T over P part. And remember, the bottom number, the P, is going to be how long for a half-life to occur. And the top number is going to be how much time has actually passed. So when I divide those two things, that's going to tell me how many half-lives have happened, right? Just tell me how many times that goes into that, right? So here's the idea. So it says Neptunium, so 235, has a half-life of 396 days. Okay, that looks like a P to me. A sample of Neptunium, 235, has a mass of this, 250 grams. So now it says write an exponential equation that models the amount Y remaining after T days. All right, here's the idea. So we're going to have, well, let's start off with our equation here. We'll say Y is equal to A, B to the power of T over P. All right, we're looking for Y, so we'll leave that as Y. And that's equal to, and here's the idea. Remember, A is where we started. That's like our Y-intercept. That started at 250. So our first number is going to be 250. And then our B value, they never actually told us, but it was written up here. We're talking half-life, so this must be a half, right? This is saying how long does it take to like cut this thing in half. So even if I just multiply these right now, right? If I went 250 times a half, that would be if this was like an X value of 1, right? That would be 1 half-life went by. But that won't be it, because we have to kind of figure that part out first. But okay, now it was T, right? That, remember, T is the amount of time that actually goes by, and the bottom number is, well, that's our actual half-life. That's how long it takes for a half-life. So that's going to be 396. And again, that's not even really any different, right? That's really just giving you X in the end, because this part is just telling you how many half-lives are going by. Okay. So that, like, this divided by this would be like a 2 or a 3 or something like that. Anyway, probably going on too long. All right, so now it says describe the transformations represented by the function in part A compared to a base function of 2 to the power of X. Okay, so we're comparing this. We're saying what happened here, right, with our transformations. Well, if we think about it here, that 250, that's our A value, right? So that is a vertical stretch, of 250 on our graph. Okay, I'll jump over to here for a second on this side, and I'm going to rewrite that for a second. Actually, let's rewrite this thing as Y is equal to 250 So times 1/2 to the power of, let's write this as 1 over 396 times t. That'd be the same thing, right? Well, okay, well that actually looks like a b value on our horizontal, or on our translations, right? Okay, well, remember that the b values are opposite of what you think. This thing actually has a horizontal stretch of the inverse of this. This is going to be 396 over 1, or just 396. And then the last one here is, it's a little bit hidden, but it asks us to compare it to the function 2 to the power of x. So I'm going to rewrite this one more time, a little bit different again. Let's write this as y is equal to 250, and I'm changing this number. Instead of 1 over 2, if we go way back and start thinking about exponent laws, 1 over 2, that can be written as 2 to the power of -1, right? That's the same thing. And then that's all times, here, 1 over 396 times t. Okay, so this -1 really could be applied to that too, right? So that's our, remember that's going to be our horizontal reflection, right? That's going to be a reflection over the y-axis, right? This negative is attached to our x in that case. So this is going to be a horizontal reflection in the y-axis. Sure. Okay. Here, I'll write it one more time. Y is equal to 250, and then times 2 to the power of, I'm just going to put this negative out with this stuff. So that's just negative, 1 over 396t, right? So now we can kind of see it, that it's attached to our x there, right? That's like a negative b value from before. Okay. Now C, what mass of Neptunium-235 remains after 1,000 days? So rounded nearest 10th. Okay, so this one would just look like this. It'd be y is equal to 250 times 1/2 for half-life to the power of, and then it's going to be, well, I'm putting the 1,000 for t now, over how long it takes for a 1/2 life, 396. And putting that all in, we would get 43.4 grams. All right, next one. When will the sample be 50? All right, so in this case, we're going to say, well, our y value, our n value is 50. And that's equal to where we started, 250. And then times 1/2 to the power of t over 396. And it's asking for t, right? Okay, well, again, the only way we can do this is by graphing. I would again recommend to do this. Go divide both sides by 250. So divide by 250. So we'd end up with 1 over 5 is equal to 1/2 to the power of t over 396. And then again, we would graph this y1 and graph this y2. Okay. And if you do that, I actually did write this one down. The answer would be, so here's our y1 and here's our y2, and they would cross at with a t value of, well, this point would be 919, comma, and then our y value here would be 1 over 5, right? So in the end, our time would be 919 days. All right, last one, compound interest. All right, so compound interest. So the formula for compound interest is a variation of the exponential growth decay formula. So compound interest, this is actually what most banks do now. There's two types of interest. There's simple interest and there's compound interest. Most banks use compound interest, and this can work either for you or it could work against you, right? Where if I'm investing money, I would like it to be compounded, like, using compound interest. And the reason for that is because what compound interest does is it takes interest on your interest. So the more interest you get, you're actually getting interest on that interest. It's saying, like, how often do they actually like look at it? And this thing looks confusing, but it's not that bad if I break it down here for a second. Here's what we got. So we'd say A is equal to P times, and then this would be 1 plus r, and let's just leave it at that for a second. Oh, sorry, n to the power of t. This equation actually looks pretty similar. We've done stuff like this, right? Remember when things went up by a certain percentage? We went like 1 plus whatever that percentage was. Like in the last example, we had 1 plus 4.5%. Okay, well, that would make sense, right? This is actually really is going to be like simple interest pretty much. Well, I guess it won't be in this case because you do it every time. But what changes here now, though, what they're doing is they're going to say, okay, let's say, well, here, let's get our variables out of the way here. A in this case is going to be how much money you're going to make. Okay, well, that makes sense. We've been kind of doing that, right? That's like our Y value from before. P is the initial value. Well, that makes sense too. That's our Y-intercept. That's where we've been starting up until now for every one of them. That's how much money you like put into your investment. R is going to be the interest rate. And then N, we haven't seen that one, but then T is the amount of time that goes by. So those ones are all should seem a little bit familiar. It's just this N value that's going to be new. So the way this is going to work is the equation is R over N, the interest rate over N. And then it's going to be N multiplied up here. But let's talk about why we have that. So things can be compounded different ways. They can be compounded annually, which would mean that you look at it once per year. This is worth looking at. So let's put a 1 in for this right now. So if that was a 1 and that was a 1, right? Then this would really just be like a typical question where you've got your interest rate going there, right? Where nothing really changes. It's just going to be per year. Whatever your interest rate for that year was, then that's what it is, right? But if we change it up and say, let's even do monthly, because that's typically how like, credit cards and stuff would be compounded. So that's 12. So what they're doing there is they're saying, okay, let's say that you had whatever your interest rate was, R, and then you divide by 12, that's going to tell you what your interest rate would be for any given month. But then what we have to do is multiply the amount of time by 12 because there's 12 months. You have to multiply that, because it's giving you the rate for 1 month, and then we have to multiply it by 12 to get to a year there, right? So that's the idea. And the reason why compounding interest works well is because when you take the exponent of something, like 12 to the power of something, that part of the equation is going to go up is going to go up faster than dividing by 12. It's like exponents trump division. Like exponents go up faster than division goes down, if that kind of makes sense. So this thing is going to gain money at a faster rate than if you just had this as being a 1, right? And if this was like 365, right? Like this was compounded daily, that would go up even faster, right? So that's the idea. And this is a really important concept to know, because when you guys start getting out, like learning about interest rates and mortgages and all that kind of stuff, when they say this thing is compounded annually or compounded daily, that makes a big difference, right? Like there's going to be a lot more. This will grow a lot faster than this one will. So you got two situations. If something is compounded daily, right, and this is money that I invested, that's great. If this thing is compounded daily and it's a credit card that I'm using, that's not great, right? That's actually money that the bank that's good for the bank. That's not good for me. So keep that in mind when you guys get out into the world. All right, so let's do this. So a student borrows $2,500 to further her post-secondary career. The bank is charging 6.5% interest compounded semi-annually. So that's 2 times a year. So write an exponential function for this. So this will just be A is equal to 2,500 times 1 plus, and then we're going to put into our equation here. So our interest rate, the only good way to write a percentage is as a decimal. So 0.065 over 2 to the power of, and then our N value is 2, and then T. Okay, so these are all just numbers in here. So you can just simplify that all up to, here, writing it all out, A is equal to 2,500, which is our principal, right? That's where we started, times 1.0325 to the power of 2 times 5. Oh, sorry, 2 times T, we'll just say for now. Okay, Getting ahead of myself. Okay, so B says if it takes the student 5 years before she can repay the loan, what amount will she be required to pay? All right. So that just really means we throw a 5 into that T, right? So we see what we get out for that one. So we'll say A is equal to 2,500 times 1.0325 to the power of 2 times 5. And then that comes out to $3,442.24. Okay, so that's how much she'll have to pay, right? Because that's just how much this number has grown in that amount of time, right? So that's that one. But then it says how much interest will she pay? Well, if this is how much there was to begin with, and then it grows to this, well, everything like extra, that was all interest. So we can just subtract those two. So we can say $3,442.24 minus 2,500, like our original, and that would be equal to $942.24. Phew. All right. Sorry, I took a bit longer than I should have on that, guys, but no, it was thorough.